Iterative versus recursive methods invocation. So since we're dealing with tree, right? So tree is a recursive data structure. We can recurse into each tree's node from the very top, which is root, all the way down to either the left or right. Sometimes both, depends on how you write your recursive algorithms. Now the question here is whether we should iteratively go through, our set of nodes, or should we write a recursion for it? We have, to this point, reviewed a number of recursive methods. Actually, there are two. One is what we call breadth first search, right? Or breadth first traversal, and the other one is a depth first, right? One involves level order traversal, visiting all of the nodes horizontally, right? And then kind of goes down that way. And the other one is depth first, right? It goes down and then back up, and then goes down and back up. So that's the difference between the two. These, every time you see a while loop, for loops involving BST, these are the recursive. These are actually the iterative methods. The recursion is a lot simpler. We use recursion, as you saw, in a binary tree traversal, either in order, post order, or pre-order, right? So those are recursive. Now, every time we're dealing with iterative mechanism, we can convert it into recursion and vice versa. So it doesn't really matter which one to use, but we're going to compare the two in this 7.5 subchapters and see which one has more merit over the other. Specifically, we're going to look at our size method, right? So this size method computes the number of nodes. So like if this is your tree, and your tree doesn't, really, it's not a lot, but it only has these nodes. The size of the tree here it's 4, okay, because there are 4 nodes. Let's say if you add another one here, you add another one here, and the size of the tree is 6, okay? So that's what we mean by size. So we're gonna write a recursive algorithms in place to find out the size of a tree. We also look at how we can use iterative methods to compute the size of the tree. So that's what we're gonna do in the next couple of pages. And then we'll do comparisons after that. So here's the recursion. Because a tree has both left and right subtrees, right? In order to set up our recursion, we want to have a placeholder, right? This is kind of our placeholder wrapper that initializes, that wraps around the recursion size algorithms. And this recursion size rec size is what we call recursive call. This is the call that's going to be called upon over and over again, right? Depends on what your entry is. So with that as our starting point, we have to understand though, the number of nodes in a tree, right, is 1, right, plus the number of nodes in the left subtree, plus the number of nodes in the right subtree, right? So generally speaking, you can have something like this. This tree branches off to more branches, things like that. And as you know, the very first top is what we call root prime, which is our root. And that is the 1 right there. Okay, that is the 1 right there. When you add up all of the nodes from the left to what's on the right, plus 1, right? So this is what's on the left, and this is what's on the right, plus that 1 right there, okay, is we have the total number of nodes in the tree. Okay, so this is the formula that we're going to abide by, and let's write some code and see what that looks like. So you probably forms a mental image of what this algorithm should look like, right? Well, if you have the rec size as our methods, and this is the recursive size, it returns an integer. This integer is the size, is the number of nodes you have in this tree. Your recursion can look like this, and basically, at every step of the way, it's checking to see if, hey, node get left is null, right? If node get right is null. If that's the case, then return 1, because that means at any step of the way, that 1 right there is your inner node, right? We call your inner node is, by the time you recurse into this point, let's say this is root, right? Root prime, R prime, right? This is your tree. This part, right, could be the 1 you're talking about, which is the inner node. This part could be the inner node as well. That's 1 right there. So if both of them are null, right, there's nothing to go with, then that node itself is 1. So you return 1 basically at the very end, and that is your basically your leaf, right? That one reg cell represents a leaf. Otherwise, return 1 plus reg size, right, all the way to the left, plus reg size all the way to the right. Here's a problem though, because we're not checking to see if node, right, at any given point is null or not. So this is going to get into the issue when you have no get left, and if null is right, null, right? So we have to do something, right, with it checking to see if node is null or not. We're not doing it, so this is not a good idea. Okay, we got some idea, but this is not the best idea. And in fact, this is gonna crash in some edge cases when null is null. So let's approach this from a second version standpoint. Now we're checking to see null is null or not, right? So that sounds kind of good, because if null is null, then return 0. Otherwise, checking to see if this returns 1. I would argue that this part is not as efficient, and that is because why would you have to check to see if the left is null, and then right, the node's right is null or not, and return a 1? So basically, I think there's a way to consolidate this into just one, right? One logic here, meaning that this part could be simplified. Now, if you look at this closely, we don't want to check, right, when this condition is met, because I don't, right? I don't have my tree in a balanced way. Sometimes the tree could be lopsided, and I don't want to compare my left and right. And sometimes maybe there's more right, there is no left. So like to get to this situation where left and right are both null, it's just one of the maybe like millions of those test cases. So writing this entire selection criteria here is redundant, right? Sometimes it does, if this is not redundant, this is extra, and it's just a waste of computing power. So if you can just generically kind of frame this entire problem as if null is null, return 0, which is fine. And then said that, the cost of doing the business is to finding all of the left and all of the right, and just let each branch, right? This is one branch and this is another branch, right? So this is one recursive call, this is another recursive call, to recursively bubble up, right, to where you are at this point. So be it. You don't have to worry about this logic anymore. So that's my point. So version 2 could be simplified. So let's take a look at the simplified version of it, which is number 3. And that's what you see inside the modules for binary search tree to Java. It's checking to see if node is null or not. If so, return 0. Otherwise, return 1 plus the recursive call into node's left subtree into its and a recursive call into this tree's right subtree, and that would get you the total number of nodes inside this tree. So this is the most efficient way of going about the business, finding out the size of the tree using a recursive algorithm. Okay. Now there's a drawback for this. Now say if the tree has millions of nodes in there, obviously you don't really want to do this. Recursive to the left and recursive, right? This presents a lot of challenges. Like I said before, when you call a function on basically it's on itself, every single call, right, into that particular function requires some stack memory space, because you have to keep track of where this function is. This is the value of backtracking, right? And backtracking requires some memory, holding power. And that memory holding power, which is your stack, is very, very limited. So you do not want to do this at runtime when there is, this height of the tree exceeds a certain amount. Okay, so that is what I wanted to preface. But let's just move on to the regex code. So this is the translation of what we talked about from pseudocode into the actual code. Okay, this entire implementations, plus, right, the wrapper size, which calls the recursive from root all the way down. And this gives you the integer that represents the number of nodes or the size of the tree. Let's move on to the next one. We can also, like I said before, without using the recursion, this recursion could be expensive when the tree height is big. Now, And this is the reason why sometimes we consider iterative versions, right? This iterative version allows you to write for loop and basically just iterate through every single level. Now, if you want to iterate through every single level of the tree, you can do this using the level order, which is the breadth first search that we talked about earlier, or you can use a depth first search, right? DFS or BFS, doesn't really matter. Either of these, as we went through them earlier, they use iterative methods that allows you to kind of write through it. So this is one example of the depth first search, right? The reason why we know that this is actually no, this is actually the breadth first search using the link stack. So let's take a look at what this is doing. So this breadth first search is a little interesting. Now we're using the stack, which is last in first out. We keep track of the left and then keep track of the right in that order. And this allows you to at every single level popping the stack, the element off of the stack. Now, this might be a little different. If you're using the Java implementation of stack, there is no top, right? There is what we call peak. And the pop itself allows you, or is what we call poll, right? POLL, that you can use these methodologies to kind of get into what you need for this one. But anyway, once you invoke this method at the end, what you get is the number of nodes that you traverse through, because at every single point, instead of printing the value out, we're counting by 1, starting with 0, as long as root is not null. So the entire mechanism is the same as what we had before. And that will go into, basically for the purpose of accounting on the size of it, using this methodology. This methodology might be a little more expensive than the previous one because now we incur this extra stack, right? Using recursion, we don't need another ADT, but using this, we require the use of another ADT in place. But recursion, sometimes could be very, very fast if the level is low, that you don't have to recurse into thousands of levels. Whereas using iterative methods, your stack is just going to keep growing and shrinking, growing, shrinking. There's the use of extra memory space that you use, and this extra memory space is in a heap. So it's slightly slower than what you would in a stack. When I say heap and stack, these are memory stack, memory heap, okay, not data structure. Anyhow, this is our iterative approach. Let's do some quick comparisons here, recursion or iteration. So generally speaking, as a rule of thumb, if your tree is small, okay, meaning maybe 50, 60, right? In general, you don't want to get into a recursion that goes on to hundreds of thousands. So if the recursion is relatively shallow, meaning the tree height is very, very low in number, yes, you should, and you could just use a recursion. And recursive solution is very, very clean, okay? It's just a couple lines versus, as you saw in a BSD implementation where the entire logic is pretty inundated. At that level, it's harder to maintain because now the developer has to understand, a bunch of code versus just a couple of lines. So this is kind of a no-brainer, right? Why would you, like, if you say recursion is more efficient, then of course you want to use recursion, but what criteria determines recursive version being more efficient? Well, generally speaking, efficiency in time and space, right? What about time? Well, if the level is short, right, meaning it's shallow, then time-wise, recursion could be just as fast as the iterative, and then you want to consider recursion. Now, the other one is space. Well, if space is not really an issue, meaning you have sufficient, that you have sufficient runtime stack memory, then that may put recursive version to be on the advantageous side versus an iterative method. So time and space, this is what I meant, time and space, okay, T and S. It both kind of are in favor of recursion. Yeah, sure. I think, with these three, especially these are two, yeah, you will want to consider recursion over the other one. Otherwise, always go back to iteration. Iteration uses mostly heap memory, which there's a ton. Even though slightly slower than the heap memory manipulations, iteration will still, serve the great purpose of finding out the size of the tree, especially when tree is super, super large. Okay, so this ends the discussions on recursion versus iteration as far as ascertaining a tree size is concerned.